Space doesn't get more comforting the further out you look. The deeper you go, the more bizarre and the more genuinely terrifying it becomes. Every layer we've peeled back has revealed something darker than the layer before it, and it doesn't stop. How far from home are you actually willing to go? If you're the kind of person who wants to truly understand what's out there, make sure to give this video a like. Now let's get started. Let's zoom out further than most people ever think to go. When astronomers map the universe at its largest scales, using surveys like the Sloan Digital Sky Survey, which has catalogued the positions of hundreds of millions of galaxies, what they see isn't a random scattering of matter. It's a pattern, a structure so precise, so geometrically consistent that it looks almost deliberately arranged. Scientists call it the cosmic web. Picture it like this. Imagine taking every galaxy in the observable universe and watching them organize themselves, not randomly, but into an intricate three-dimensional lattice. Long filaments of matter, enormous threads made up of galaxies, gas and dark matter, stretch across hundreds of millions of light years. Where multiple filaments intersect, gravity pulls everything together into massive nodes, galaxy clusters and superclusters, the densest, most energetic regions in all of existence. And between the filaments, between the nodes, between all that structure, almost nothing. Enormous empty regions called voids, stretching hundreds of millions of light years in every direction, containing only a tiny fraction of the matter found in the filaments. This is the universe at its true scale. Not a scattering of stars, a web. And the more we study it, the more it raises questions that don't have clean answers. Let's start with the filaments themselves, because they are genuinely staggering. The largest known filament in the observable universe is called the Hercules Corona Borealis Great Wall. Discovered in 2013 and confirmed through subsequent studies, it spans an estimated 10 billion light-years in length. 10 billion. The observable universe itself is only about 93 billion light-years in diameter. This one structure takes up roughly a tenth of the entire observable universe in one dimension alone. Now here's the problem, and this is important. The existence of a structure that large actually challenges something called the cosmological principle, one of the foundational assumptions of modern cosmology. The cosmological principle states that, on large enough scales, the universe is roughly uniform. Matter should be spread out roughly evenly when you zoom out far enough. There shouldn't be enormous concentrations of matter dominating entire sections of the observable universe, but the Hercules Corona Borealis Great Wall says otherwise. It's too big. It shouldn't have had enough time to form given the current age of the universe. Approximately 13.8 billion years. The gravitational processes that pull matter together into filaments work over enormous timescales, and forming a structure 10 billion light-years across in 13.8 billion years doesn't comfortably fit our models. Some researchers argue the structure may be a statistical artifact, a pattern that appears significant but may not represent a truly bound structure. Others maintain it is genuinely one of the largest coherent structures ever identified. The debate continues, and that tension between what our models predict and what our telescopes actually see is one of the most exciting and unsettling threads running through modern cosmology. It isn't the only one. In 2022, a team of astronomers announced the discovery of something called the Big Ring. It's a nearly perfect ring-shaped arrangement of galaxies, about 1.3 billion light-years in diameter, sitting roughly 9.2 billion light-years from Earth. Around the same time, the same lead researcher, Alexia Lopez of the University of Central Lancashire, had also identified another massive structure called the Giant Arc, stretching roughly 3.3 billion light-years across. Neither structure fits neatly into standard cosmological models. Neither was predicted. Both are sitting there in the data, confirmed by multiple analyses, waiting for an explanation that fully satisfies everyone. Some theorists have suggested these ring-like and arc-like patterns might be the echoes of acoustic waves that rippled through the early universe, what cosmologists call baryon acoustic oscillations. Others think they could be something else entirely, something we don't yet have a complete theoretical framework to describe. What's remarkable is that these discoveries keep coming. Every time we build a better telescope, map a deeper region of the sky, or develop a more sensitive instrument, the universe hands us something that doesn't quite fit what we expected, not always dramatically, not always in a way that overturns everything, but persistently, quietly, as if the cosmos is always slightly ahead of whatever model we've constructed to describe it. Now let's talk about the voids, because they deserve their own moment. When most people think about empty space, they imagine the gaps between stars within a galaxy, regions that are, relatively speaking, not that empty at all. A galaxy is a crowded place on a cosmic scale, but cosmic voids are something else entirely. These are regions between the filaments of the cosmic web where the density of matter drops to almost nothing. No galaxy clusters, barely any galaxies at all in some cases. Just an enormous stretch of near-nothingness that can span hundreds of millions of light years in every direction. The largest confirmed void is the Boötes Void, discovered in 1981. It stretches roughly 330 million light-years across. When astronomers first found it, they were stunned, not just by its size, but by how empty it was. A region that large, according to the standard models of structure formation, should contain thousands of galaxies. Instead, it held only about 60. Some counts put it even lower. Astronomers started calling it the Great Nothing, and some of them, not entirely seriously but not entirely not, began asking whether something had cleared it out. Nothing plausible, nothing scientifically supported at the time. But the question had a weight to it. Here's what we do know. Voids are not just passive empty regions, they're dynamic. Matter near the edges of voids tends to be slowly drained outward by gravity from the surrounding filaments, which gradually hollows out the interior even further over billions of years. So voids grow emptier over time as the cosmic web pulls matter into its threads. The Boötes Void is almost certainly still growing, and inside voids, even the emptiest ones, there are still tiny traces of matter. Very faint, very sparse galaxy populations, sometimes called void galaxies. These galaxies, sitting almost completely isolated from any cosmic structure, evolve differently from galaxies embedded in clusters or filaments, without neighbors, without major mergers, without the gravitational chaos of a dense environment. Some void galaxies remain oddly pristine, almost frozen in an early stage of development, like they never quite got the memo that several billion years had passed. But there's one void that stands apart from all the others, and it's not the Boötes Void. In 2004, astronomers using the Wilkinson Microwave Anisotropy Probe, a NASA satellite designed to map the cosmic microwave background, the faint thermal afterglow of the Big Bang, noticed something unexpected. There was a region in the CMB map significantly colder than its surroundings, not drastically colder, but measurably, persistently, reproducibly colder. It came to be known as the cold spot. The cold spot sits in the direction of the constellation Eridanus, and it's been confirmed by multiple independent observations since, including data from the European Space Agency's Planck satellite. It covers a region of the sky about 5 degrees across, roughly 10 times the width of the full moon, and its temperature is about 70 microkelvins below the surrounding CMB average. That might sound like a tiny difference, and on one level it is, but in the context of the CMB, which is itself only about 2.7 Kelvin above absolute zero, and remarkably uniform, that deviation is significant, and it demands an explanation. The leading mainstream explanation is that the cold spot corresponds to a massive supervoid, an enormous underdense region of space that photons from the CMB had to travel through. As photons pass through a void, they lose a tiny bit of energy in a process called the integrated Sachs-Wolf effect. A big enough void could produce the kind of cold signal we see, and in 2015, a team led by Istvan Sapudi at the University of Hawaii found exactly that. A supervoid about 1.8 billion light-years across, aligned with the cold spot. It was one of the largest voids ever identified. A supervoid that could, in their calculations, account for about 10 to 20% of the cold spot's temperature deficit. 10 to 20%, not all of it. The rest remains unexplained, which brought some physicists back to a different hypothesis. A stranger one that mainstream cosmology treats with caution but hasn't been able to fully rule out. The cold spot, some have suggested, might be the imprint of another universe, the many worlds interpretation of quantum mechanics, and separately, inflation theory and cosmology. Both leave room, mathematically speaking, for the existence of other universes beyond our own. In certain inflationary models, our universe is just one bubble in a vast multiverse of bubbles, each nucleating from a rapidly expanding quantum field in the early moments after the Big Bang. If our bubble and another bubble had collided in those earliest instants, the collision might have left a detectable imprint on the cosmic microwave background, a bruise, a cold patch. Is that what the cold spot is? Almost certainly not. The supervoid explanation is more parsimonious and more consistent with known physics. But it doesn't fully account for the anomaly, and so the door, however narrow, has not been fully closed. We are, in the most literal sense, looking at the edge of our own observable universe, reading the faint glow of ancient light, and finding patterns we can't completely explain, patterns that might be mundane, or might be something much more profound. That's where we are, and we've barely started. Stay with me, let's talk about the most luminous objects in the observable universe, not stars, not galaxies, not supernovae, something far more extreme than any of those. Something so bright, so energetic, so overwhelmingly powerful that for decades after their discovery, scientists had absolutely no idea what they were looking at. We call them quasars. The name comes from quasi-stellar radio source, because when astronomers first detected them in the 1960s, they appeared in telescopes as single points of light, almost indistinguishable from stars. Except they weren't stars, they were radiating energy at levels no star could ever produce. And they were sitting at cosmological distances, billions of light years away, which meant that to appear as bright as they did from that far out, they had to be generating something almost incomprehensible in terms of raw power output. It took years of observation, debate, and theoretical work before a consensus emerged. What we were seeing wasn't a star. It was the core of a distant galaxy, specifically a galaxy with a supermassive black hole at its center, in a state of intense, violent activity. Gas, dust, and stellar material were falling into the black hole at enormous rates, and as that material spiraled inward through what's called an accretion disk, it heated up dramatically. Friction, compression, and magnetic forces superheated that infalling matter to temperatures of billions of degrees. At those temperatures, matter doesn't just glow. It radiates across the entire electromagnetic spectrum, visible light, ultraviolet, X-rays, even gamma rays, with a ferocity that can outshine every single star in the host galaxy combined. By factors of hundreds, sometimes thousands, the most luminous quasars ever observed outshine their entire host galaxies by a factor of up to 100 times. A single object, one black hole and its surrounding disk of infalling matter, generating more light and energy than hundreds of billions of stars put together. The current record holder for the most luminous object ever discovered is a quasar called J0589+0134, identified using the Very Large Telescope in Chile and announced in early 2024. It's powered by a black hole consuming the equivalent of roughly one solar mass, one entire sun's worth of matter, every single day. Its luminosity is estimated at 500 trillion times that of our Sun. 500 trillion. And it sits about 12 billion light-years away, meaning we're seeing it as it existed when the universe was less than 2 billion years old. Think about what that means. Less than 2 billion years after the Big Bang, a black hole had already grown to a mass of 17 billion suns and was actively tearing through its surrounding material at a rate that defies easy comprehension. How a black hole gets that massive that quickly is itself one of the great unsolved problems in astrophysics. Our current models of black hole growth, which rely on relatively steady accretion and occasional mergers, struggle to produce objects that large in that shorter time frame. Yet there they are, sitting in the data, demanding an explanation we don't fully have. Now quasars are ancient. Most of the ones we observe existed in the early universe, the first few billion years. When galaxies were younger, gas was more abundant, and the conditions for feeding a supermassive black hole were far more common. As the universe aged, galaxies consumed their available gas, star formation slowed, and most of the fuel for those extreme feeding events dried up. The era of quasars largely came to a close. The supermassive black holes that powered them didn't disappear. They're still there, sitting at the centers of most large galaxies, including our own. They just quieted down, but some of them didn't. Some supermassive black holes are still active today, still feeding, still radiating. We call these active galactic nuclei, or AGN. Quasars are the most extreme version, but there's another class that's arguably even more alarming: blazars. A blazar is what you get when an active galactic nucleus happens to be pointed almost directly at Earth. When a supermassive black hole is actively feeding, it often generates two enormous jets of plasma, streams of superheated, magnetically confined material that shoot outward from the poles of the black hole at velocities approaching the speed of light. These jets can stretch for millions of light years. When one of those jets is aimed almost straight at us, the radiation we receive is dramatically amplified by a relativistic effect called Doppler boosting. The result is an object of almost surreal brightness, variable on timescales of hours, sometimes minutes, flickering across the entire electromagnetic spectrum as the jet churns and fluctuates. Some blazars are so energetic they produce gamma rays with energies millions of times greater than visible light. When instruments like the Fermi Gamma Ray Space Telescope detect a blazar flare, what they're registering is a beam of high-energy radiation from a jet produced by a black hole billions of light-years away, a jet that has been traveling across the cosmos for billions of years and happens to be aimed almost perfectly at the tiny patch of sky our telescopes occupy. The universe, at its most extreme, shoots beams of high-energy radiation across billions of light-years, and occasionally one of them is pointing right at us. Now let's slow down for a moment, because to really understand what makes black holes so deeply unsettling, not just as sources of energy, but as objects in space, we need to talk about what they actually do to the universe around them. Not just in terms of energy output. In terms of space-time itself, you've probably heard that black holes have such powerful gravity that nothing, not even light, can escape past the event horizon. That's true. But it leaves out the part that most people find genuinely difficult to sit with once they've really thought it through. The event horizon of a black hole is not a physical surface. It's not a wall. It's not a membrane. It's a boundary defined purely by geometry, the point at which the curvature of space-time becomes so extreme that all possible paths through space, including the path light takes, curve back inward, Past the event horizon, every direction you can move, forward, backward, sideways, any direction at all, leads deeper into the black hole. There is no outward direction anymore. Space itself has become a one-way street, and the destination is the singularity. Now, here's what makes this so strange. From the perspective of someone falling into a large enough black hole, a supermassive one, like the ones we've been discussing, they might not notice anything dramatic at the moment they cross the event horizon. The tidal forces at the event horizon of a truly massive black hole are actually manageable for the human body. You wouldn't be torn apart. You wouldn't feel a sudden change. You would simply cross a mathematical boundary in space and continue falling, and yet, from the perspective of someone watching you fall from far outside the black hole, something completely different happens. Due to the extreme gravitational time dilation near the event horizon, light from you takes longer and longer to escape and reach the distant observer. You appear to slow down. Your image redshifts, shifts toward longer, redder wavelengths as the photons climbing out of that deep gravity well lose energy. To the outside observer, you appear to freeze at the event horizon, gradually fading and redshifting into invisibility. You never appear to cross it. Two observers, two completely different and irreconcilable experiences of the same event, both described accurately by the physics of general relativity. This isn't a paradox that gets resolved cleanly. It's one of the places where general relativity and quantum mechanics, our two greatest theories, come into direct conflict with each other, and neither is willing to give ground. That conflict goes even deeper when you bring in what Stephen Hawking proposed in 1974. Using a combination of quantum field theory and curved space-time geometry, Hawking showed mathematically that black holes aren't entirely black. They radiate very slowly, very faintly, but they emit what's now called Hawking radiation, a consequence of quantum effects near the event horizon. And because they radiate, they lose mass. Over unimaginably long timescales, a black hole radiates away its entire mass and eventually evaporates entirely. Now here's the problem that makes physicists genuinely uncomfortable. When a black hole forms, it swallows matter, matter that carries information, the quantum state of every particle that falls in. And according to quantum mechanics, information cannot be destroyed. It's one of the foundational principles of the theory. Information is always conserved. It can be scrambled, hidden, encoded, but never deleted. But if a black hole evaporates completely through Hawking radiation, and that radiation appears to be essentially random, carrying no coherent information about what fell in, then where did all that information go? This is the black hole information paradox, and it remains one of the deepest unsolved problems in theoretical physics. Some of the greatest minds of the last 50 years have grappled with it. Hawking himself changed his position on it multiple times throughout his life. Various solutions have been proposed: firewalls at the event horizon, holographic encoding on the black hole's surface, new forms of quantum gravity, but none has achieved full consensus. We built the most powerful theory of gravity ever conceived, general relativity, and the most successful theory of matter and energy ever developed, quantum mechanics. And when we put them together in the environment of a black hole, they break each other. That's where physics stands, right now, today. And yet, for all the violence, for all the paradoxes, for all the things about black holes that resist our best attempts at understanding, there's something else worth sitting with. Something that pulls in the opposite direction from terror. We know black holes exist not just from theory now, we've seen them. In April 2019, the Event Horizon Telescope, a planet-spanning array of synchronized radio telescopes functioning as a single Earth-sized dish, produced the first direct image of a black hole's shadow. The target was M87 star, the supermassive black hole at the center of the Messier 87 galaxy, sitting about 53 million light-years away. Its mass, 6.5 billion times that of our Sun, and then in 2022, the same collaboration turned its gaze inward, toward the center of our own galaxy, and captured an image of Sagittarius A star, our black hole. 4 million solar masses, sitting 26,000 light-years from Earth, surrounded by a glowing ring of superheated gas. We didn't just theorize it, we photographed it. Humanity coordinated telescopes across multiple continents, synchronized them to fractions of a second, and captured light from the edge of something that swallows light. That is one of the most extraordinary things our species has ever done. And it confirmed, in visual terms that anyone can look at, that these objects are real. They're there. Our galaxy has one at its heart. Let's go back. Further back than anyone usually thinks to go. Not to the beginning of Earth, not to the formation of our solar system, not even to the birth of the first stars. Let's go all the way back to the very first moment, the first sliver of time after the universe came into existence. And I mean a sliver in the most literal sense possible. We're talking about the first 10 to the power of -43 seconds. A unit of time so small it doesn't even have a clean name in everyday language. Physicists call it the Planck time. It's the smallest meaningful unit of time that current physics can describe. Before it, our equations don't just struggle, they collapse entirely. That boundary, that wall at the very beginning of everything, is one of the most confronting edges in all of science, not because we lack the data, but because the framework we'd need to even ask the right questions about it doesn't fully exist yet. General relativity, which governs the large-scale structure of space-time, and quantum mechanics, which governs the behavior of matter and energy at the smallest scales. Neither one works at the conditions present in those first instants. The density and temperature of the entire universe compressed into a volume smaller than a single proton overwhelms both theories simultaneously. We are, in a very real sense, standing at the edge of what human knowledge can currently reach, and staring into a fog we haven't yet built the tools to lift. But here's what we do know, or at least what our best models strongly suggest. In the fraction of a second following the Planck time, something extraordinary happened, something so dramatic that it reshaped the entire structure of the cosmos and set the stage for everything that came after. Cosmologists call it inflation. Inflation is the idea, first formally proposed by physicist Alan Guth in 1980, that in an incredibly brief window of time, somewhere between 10 to the -36 and 10 to the -32 seconds after the Big Bang, the universe underwent a period of exponential expansion, not the steady, gradual expansion we observe today, something far more violent. The universe grew by a factor of at least 10 to the power of 26, possibly far more, in a time so short it makes a billionth of a second look leisurely. To put that in some kind of perspective, imagine something the size of a proton expanding to roughly the size of the observable universe in less time than it takes light to cross a single hydrogen atom. That's the scale of what inflation theory proposes. And before you dismiss it as pure speculation, consider what it actually explains. Before inflation was proposed, cosmologists faced several deep puzzles that standard Big Bang theory couldn't resolve on its own. Why is the cosmic microwave background, that ancient glow of light from the early universe, almost perfectly uniform in temperature across regions of the sky, that, given the age of the universe, should never have been in contact with each other? They're too far apart. Light couldn't have traveled between them in the time available. So how do they know to be the same temperature? This is called the horizon problem. Inflation solves it by proposing that all those regions were once in contact. They were all part of a tiny, causally connected region before the exponential expansion stretched them apart. Similarly, Why is the universe's geometry so flat? General relativity allows for curved universes, positively curved like the surface of a sphere, or negatively curved like a saddle. But observations consistently show that our universe is flat to extraordinary precision. Without inflation, producing that flatness would require almost impossibly fine-tuned initial conditions. Inflation naturally drives the geometry toward flatness, the same way the surface of an expanding balloon appears increasingly flat as it grows. And there's a third thing inflation explains, and this one is remarkable: the large-scale structure of the universe, the filaments, the voids, the galaxy clusters, the entire cosmic web we talked about. All of it traces back to tiny quantum fluctuations in the inflationary field. Microscopic variations in energy density, stretched by inflation to cosmic scales, became the seeds of everything, every galaxy, every star, every planet, every living thing. The origin of all that structure lies in quantum randomness during a fraction of a second at the dawn of time. You are the grown-up version of a quantum fluctuation, but inflation raises a question that's even harder to sit with than the problems it solves. And it's this: if the universe underwent a period of exponential expansion, what caused inflation to end? In most models, inflation is driven by a hypothetical field, the inflaton field, whose energy density drove the expansion. When that field reached a certain low-energy state, inflation ended. The energy stored in the field was converted into the hot, dense plasma of particles and radiation that we associate with the conventional Big Bang. This moment is sometimes called reheating, the point at which the universe, cooled by expansion, was suddenly flooded with energy again and began the slower, more familiar story of cosmic evolution. But here's where it gets philosophically vertiginous. In many inflationary models, including the ones that best fit the observational data, inflation doesn't end everywhere at once. Different regions of the inflating space reach the low-energy state at different times. In the regions where inflation ends, you get a universe like ours. But in the surrounding regions, inflation continues. And as it continues, it generates more space, more regions, more potential bubble universes, each nucleating at a different moment with potentially different physical properties. This is eternal inflation. The idea that inflation, once started, never fully stops, that it continues producing new pocket universes indefinitely, each one causally disconnected from all the others. Our observable universe would be just one of an incomprehensibly vast, possibly infinite, ensemble of universes, each born from a bubble in an eternally expanding sea of inflationary space. This is not fringe science. Eternal inflation follows mathematically from some of the most well-supported models of the early universe. Alan Guth, André Linde, and others who built the theoretical foundations of inflation have written extensively about it. It is a genuine, seriously considered framework in theoretical cosmology. But it comes with a deeply uncomfortable consequence. If the multiverse is real, if inflation produces an effectively infinite number of pocket universes, then the specific physical constants we observe in our universe, things like the strength of gravity, the mass of the electron, the value of the cosmological constant, may not be uniquely determined by any deeper law. They may simply be the values our particular bubble happened to land on, random, accidental, selected not by necessity, but by the fact that only certain combinations of constants allow for stars, planets, chemistry, and observers to exist in the first place. This is called the anthropic principle, and for many physicists it feels deeply unsatisfying. Science aspires to explain why things are the way they are. The anthropic argument essentially says, they are this way because if they weren't, you wouldn't be here to ask. It's logically coherent, and it's philosophically maddening. Now let's talk about what was discovered in 2023. Because this is genuinely one of the most significant astronomical announcements of the last decade, and it didn't get nearly the attention it deserved. For years, physicists had been searching for something called the gravitational wave background, sometimes called the gravitational wave hum. You may have heard about gravitational waves from the landmark LIGO detection in 2016, when two merging black holes sent ripples through space-time that reached Earth and were detected for the first time. That was extraordinary. But those were individual events, discrete gravitational wave signals from specific mergers. The gravitational wave background is different. It's not a signal from any single event. It's the accumulated gravitational wave output of every supermassive black hole merger, every cataclysmic collision, every violent event across the entire history of the observable universe, all overlapping and blending into a continuous low-frequency rumble that permeates all of space-time, like the background noise of a city, except the city is the entire universe and the noise is ripples in the fabric of reality. Detecting something like that requires extraordinary precision. LIGO, as remarkable as it is, operates at too high a frequency to hear it. What you need instead is a different kind of detector, one that uses pulsars. Pulsars are rapidly rotating neutron stars that emit beams of radio waves with extraordinary regularity. Some millisecond pulsars are so precise in their timing that they rival atomic clocks. By monitoring arrays of these pulsars spread across the galaxy, what astronomers call pulsar timing arrays, and looking for correlated, subtle shifts in their timing that affect all of them simultaneously, you can effectively use the galaxy itself as a gravitational wave detector. In June of 2023, 4 major pulsar timing array collaborations from North America, Europe, China, and India, Australia, simultaneously announced that they had found it, the gravitational wave background, a correlated signal across dozens of pulsars, consistent with the signature of low-frequency gravitational waves washing through our galaxy, through us. Right now, as you watch this, the space-time you're sitting in is vibrating very gently, very slowly, stretched and compressed by the accumulated gravitational echoes of billions of years of cosmic violence, supermassive black holes colliding in distant galaxies, sending ripples across the universe that are only now, after traveling billions of light years, passing through the Milky Way. We are soaking in gravitational waves. We always have been. We just learned to hear them. The implications are significant in ways that will take years to fully unpack. The amplitude and shape of the gravitational wave background carries information about the population of supermassive black hole binaries across cosmic history, how many there are, how massive they are, how frequently they merge. It may also contain information about processes in the very early universe, phase transitions, cosmic strings, or other exotic phenomena from the first moments after the Big Bang. As pulsar timing arrays collect more data and sensitivity improves, they may be able to disentangle individual contributions to that background hum and read the history of cosmic violence written into space-time itself. There's even a possibility, highly speculative but not dismissible, that the background contains a contribution from inflation itself. Inflation would have produced gravitational waves. Those waves, stretched to enormous scales by the expansion of the universe, would today occupy frequencies far below what any current detector can reach. But they're there in principle, and if we can ever detect them directly, if we can hear the gravitational echo of the inflationary epoch, it would be the closest thing to direct observational evidence of what happened in those first extraordinary fractions of a second. We would be listening to the birth cry of the universe, and yet, even all of this, the Big Bang, inflation, the gravitational wave background, the multiverse, describes only the matter and energy we can directly observe or infer from known physics. It leaves out the majority of what the universe is actually made of, because when you add up all the ordinary matter, every star, every planet, every atom of gas, every grain of dust across the entire observable universe, it comes to roughly 5% of the total energy content of the cosmos. 5%. The remaining 95% is divided between two things we can detect only through their effects on ordinary matter. We call them dark matter and dark energy, and now we're going to confront them directly. Because dark energy in particular does something to the future of the universe that, once you understand it clearly, is very hard to unfeel. The universe has an expiration date, and the way it ends is stranger and lonelier than almost anything else we've discussed. 5%, let that sit for a moment. Every star you've ever seen in the night sky, every galaxy in every image ever taken by the Hubble or James Webb Space Telescopes, every atom in your body adds up to roughly 5% of what's actually out there. The rest is something else entirely. If you are enjoying this journey, make sure to subscribe and give this video a like. Every day, this channel gives you the universe the way it actually is. If that's the kind of content you live for, you're already home. And the uncomfortable truth is that despite decades of research, billions of dollars in experiments, and some of the most brilliant minds our species has ever produced working on the problem, we don't know what that something else is. Not really. We know what it does. We can map its effects with extraordinary precision, but its fundamental nature remains one of the deepest unsolved mysteries in all of physics. Let's take them one at a time. Because they are genuinely different things with different implications, and it's worth understanding each one clearly. Dark matter first. The story of dark matter goes back further than most people realize. As early as 1933, Swiss astronomer Fritz Zwicky was studying the Coma cluster, a large collection of galaxies, and noticed something deeply wrong with the math. The galaxies in the cluster were moving far too fast. Based on the visible mass of all the galaxies combined, the gravitational pull holding the cluster together shouldn't have been nearly strong enough to keep those galaxies from flying apart. The cluster should have been dispersing. It wasn't. Zwicky proposed that there must be additional invisible mass providing the extra gravitational glue. He called it Dunkel Materiae, dark matter, and he was largely ignored for decades. Then in the 1970s, astronomer Vera Rubin, working with her colleague Kent Ford, began measuring the rotation curves of spiral galaxies. Here's what she expected to find. Stars near the outer edges of a galaxy, far from the concentrated mass at the center, should orbit more slowly than stars closer in, just like the outer planets in our solar system orbit the Sun more slowly than the inner ones. That's basic Newtonian gravity. The more distance, the weaker the pull, the slower the orbit. What she actually found was something completely different. The rotation curves were flat. Stars at the outer edges of galaxies were orbiting at roughly the same speed as stars much closer to the center, not slowing down at all, as if they were embedded in a much larger, more diffuse mass distribution that extended well beyond the visible galaxy, a vast invisible halo surrounding each spiral galaxy and providing enough additional gravitational influence to keep those outer stars moving fast. Rubin's findings were meticulous, reproducible, and ultimately impossible to dismiss. Combined with Zwicky's earlier cluster observations, gravitational lensing data, which shows light from distant galaxies being bent by invisible mass, and detailed maps of the cosmic microwave background, the evidence for dark matter had become overwhelming by the late 20th century. Something is there. It interacts gravitationally. It doesn't emit, absorb, or reflect light. It clusters around galaxies and galaxy clusters, forming invisible halos that far outmass the visible structures they surround. And based on cosmological measurements, there's roughly 5 times more of it than ordinary matter. about 27% of the total energy content of the universe, but what is it physically? That's where things get genuinely difficult. The leading candidates for decades were particles called WIMPs, weakly interacting massive particles. The idea was elegant. If dark matter consists of heavy particles that interact via gravity and the weak nuclear force, but nothing else, they'd be invisible to telescopes, pass through ordinary matter almost without interaction, and naturally produce the right abundance in the early universe through a process called thermal freeze-out. Better yet, WIMPs were predicted to exist independently by supersymmetry, a theoretical extension of the standard model of particle physics that many physicists considered almost inevitable, so experiments were built. Underground detectors filled with liquid xenon or germanium crystals, shielded from cosmic rays by kilometers of rock, waiting for the rare moment when a dark matter particle might scatter off an atomic nucleus and leave a detectable recoil. The Large Hadron Collider at CERN searched for WIMP signatures in high-energy collisions. Satellites and telescopes hunted for the gamma rays that WIMPs should produce when they annihilate each other. Nothing. Decade after decade of increasingly sensitive experiments. The parameter space where WIMPs can hide has been squeezed dramatically. The simplest, most natural versions of WIMP dark matter are essentially ruled out now. Supersymmetric particles have not appeared at the LHC despite extensive searching. The elegant solution hasn't materialized. This doesn't mean dark matter isn't real. The gravitational evidence for it is ironclad. It means we were probably wrong about what it is. And the alternatives are genuinely diverse. Axions, extremely light particles originally proposed to solve a completely unrelated problem in quantum chromodynamics. Primordial black holes formed in the very early universe before any stars existed, possibly making up some fraction of the dark matter. Sterile neutrinos, fuzzy dark matter, an idea in which dark matter consists of ultralight particles with quantum wavelengths so large they smooth out structure on small scales. Each of these has its own experimental signature, its own set of predictions, its own community of researchers hunting for evidence. We are, right now, in the middle of one of the greatest detective stories in the history of science. The suspect is confirmed. The crime scene is the entire universe, but the identity of the perpetrator remains unknown. Now, dark energy. If dark matter is strange, dark energy is in a category of its own. Because dark matter, however mysterious, is at least something. It has mass, it gravitates, it participates in the universe's structure in recognizable ways. Dark energy is different in kind, not just in degree, and what it does to the universe, what it is doing right now, and what it will continue doing for the rest of time, is one of the most profound and unsettling things physics has ever uncovered. Here's the background. In 1998, two independent teams of astronomers, the High-Z Supernova Search Team and the Supernova Cosmology Project, were using a particular type of exploding star called a Type Ia supernova as a cosmic distance marker. Type Ia supernovae are remarkably consistent in their peak luminosity, which makes them useful as what astronomers call standard candles. By comparing how bright they appear against how bright they should be at a given distance, you can precisely map the expansion of the universe across cosmic time. Both teams expected to find that the expansion of the universe was slowing down. Gravity pulls matter together. Common sense and the physics of the time suggested that the mutual gravitational attraction of all the matter in the universe should be gradually applying the brakes to the expansion that began at the Big Bang. Instead, both teams found the opposite. The distant supernovae were dimmer than expected, not because something was blocking the light, but because they were further away than they should have been. The expansion of the universe wasn't slowing down. It was speeding up. The universe is accelerating, Space itself is expanding faster and faster with every passing moment, and something is driving that acceleration, something with negative pressure, something that, unlike matter, doesn't dilute as space expands, but instead maintains a constant energy density even as the volume of the universe grows. This discovery was so shocking, so contrary to expectation, that the three lead researchers, Saul Perlmutter, Brian Schmidt, and Adam Riess, were awarded the Nobel Prize in Physics in 2011. We call the thing driving the acceleration dark energy. It makes up roughly 68% of the total energy content of the universe, and we have essentially no idea what it fundamentally is. The simplest mathematical description of dark energy is Einstein's cosmological constant, a term he originally introduced into his equations of general relativity in 1917 to produce a static universe, then famously abandoned when Edwin Hubble demonstrated that the universe was expanding. Einstein called the cosmological constant his greatest blunder. As it turns out, something very much like it appears to be real, just not for the reason Einstein originally proposed it. In quantum field theory, empty space isn't actually empty. Virtual particles constantly pop in and out of existence, and this quantum activity gives the vacuum a non-zero energy density. When physicists calculate what that vacuum energy density should be using quantum field theory and then compare it to the observed value of the cosmological constant, they get a discrepancy of somewhere around 120 orders of magnitude. That is the largest discrepancy between a theoretical prediction and an observational measurement in the entire history of physics, by an almost incomprehensible margin. It's called the cosmological constant problem, and it remains completely unresolved. So we know dark energy exists. We can measure its effects to high precision. We know it makes up most of the universe. We have a mathematical placeholder for it in our equations. And we have essentially no physical understanding of what it actually is or why it has the value it does. What we do know is what it's doing and what it will continue to do. Because of dark energy, the universe is not just expanding, it's expanding at an accelerating rate. And as that acceleration continues, something deeply strange begins to happen to the observable universe itself. Right now, the observable universe, the region from which light has had time to reach us since the Big Bang, spans about 46 billion light-years in every direction. But beyond that boundary, there are galaxies we can't see yet. Galaxies whose light is still traveling toward us and hasn't arrived. Given enough time, that light would reach us and our observable horizon would expand, except it won't. Because the galaxies beyond a certain distance are already receding from us faster than light can cross the gap. Not because they're moving through space at faster than light speed, that would violate relativity, but because the space between us and them is expanding, and the cumulative rate of that expansion exceeds the speed of light over large enough distances, those galaxies are not just unreachable, they are progressively, permanently, irreversibly vanishing beyond our cosmic horizon, and as dark energy drives the acceleration further, that horizon shrinks. More and more galaxies that are right now observable, right now visible to our telescopes, will eventually recede beyond the point where their light can ever reach us again. In roughly 150 billion years or so, the only galaxies a civilization in the Milky Way would be able to see are those gravitationally bound to us in the local group. Everything else, the hundreds of billions of other galaxies we can observe today, will be gone, not destroyed, just unreachable, invisible, as if they never existed. An observer in the far future, with no record of our current observations, would look out at the night sky and see almost nothing beyond their own galaxy cluster. They would have no way of knowing the universe contained hundreds of billions of other galaxies. They might conclude they were alone, and they would have no way to prove otherwise. We happen to live at a privileged moment in cosmic history, early enough that the universe is still young and visible enough for us to see its full grandeur. That window is closing, very slowly, but closing nonetheless, and further down the timeline, things get even lonelier. Eventually, on timescales almost too vast to speak meaningfully about, the stars will burn out. The last red dwarf stars, the most long-lived of all stellar types, will exhaust their fuel in something like 10 to the power of 14 years, 100 trillion years from now. After that, no new stars form. The galaxies go dark. What remains are black holes, neutron stars, white dwarfs, slowly cooling toward absolute zero, and the occasional dead remnant of what were once living, burning suns. Then the black holes begin to evaporate. Through Hawking radiation, that impossibly slow quantum process we discussed in a while ago, even the most massive black holes will eventually radiate away their entire mass. The largest supermassive black holes won't complete this process for something like 10 to the power of 100 years, a number so large there isn't a word for it in common usage. A 1 followed by 100 zeros after that, a universe of maximum entropy, cold, uniform, dark, no gradients of temperature or energy left to drive any process, no stars, no planets, no black holes, no structure of any kind. Just an infinite, featureless expanse of cold radiation and isolated subatomic particles, expanding forever into a void with no meaningful distinction between one region and another. Physicists call this the heat death of the universe, the final state of everything, not a dramatic explosion, not a crunch back to a singularity, just a slow, quiet, irrevocable fading into uniformity and darkness. And the thing that makes it so hard to sit with isn't the timescale, it's the completeness. Everything that ever happened, every star that ever burned, every civilization that ever arose, every thought ever thought, every piece of music ever composed, every act of love or courage or discovery, all of it, in the longest possible view, ends in the same cold, undifferentiated silence, unless something changes. Unless physics contains surprises we haven't found yet. Unless the universe, which has already surprised us more times than we can count, has something else in store that no current theory predicts. That possibility that we might be missing something fundamental is not wishful thinking. It's the honest assessment of where we are. The history of science is a history of incomplete maps. And the universe has never once failed to be stranger than our best current model suggested. Let's take everything we've built, the cosmic web, the black holes, inflation, dark energy, the fate of the universe, and push into the territory that even most physicists find genuinely disorienting. We're going to talk about the nature of time itself, about whether the past is real, about a discovery from 2023 that suggests the universe may not be as smooth and continuous as we thought, and about something called the simulation hypothesis, not as science fiction, but as a serious, mathematically grounded question that several prominent physicists have engaged with in peer-reviewed literature, because at a certain depth of inquiry, the universe stops feeling like a place you're observing from the outside and starts feeling like something you might be inside of in a much more fundamental way than you ever imagined. Stay with me. Let's talk about time, not in the abstract philosophical way people usually mean when they say that, not in the sense of wondering where the years went or why the days feel short. Let's talk about time the way physics talks about it. Because the moment you look at what our best theories actually say about the nature of time, something deeply strange emerges. Something that most people never encounter, even though it sits right at the foundation of our most successful scientific frameworks. Here's the thing that took physicists a long time to fully reckon with. The fundamental equations of physics, the ones governing quantum mechanics, general relativity, electromagnetism, even classical mechanics, are almost entirely time-symmetric. Run them forward, they work. Run them backward, they still work. The mathematics doesn't care which direction time flows. A video of two billiard balls colliding looks physically valid whether you play it forward or in reverse. The equations permit both equally. And yet you have never seen a broken egg spontaneously reassemble itself. You have never watched smoke pour back down into a chimney and reform into wood. You have never experienced a memory of the future. Time, in your experience and in everything you observe around you, flows in one direction only, from past to future, always, without exception. So where does that arrow come from? If the underlying laws of physics are symmetric in time, why does the universe we actually live in have such a dramatic, unambiguous direction to it? The standard answer involves entropy, the measure of disorder in a system. The second law of thermodynamics states that in a closed system, entropy tends to increase over time. Things fall apart. Order dissolves into disorder. Heat flows from hot to cold, never the reverse. And the arrow of time we experience, the reason the past feels fixed and the future feels open, is essentially the arrow of increasing entropy. But that answer, satisfying as it sounds at first, immediately raises a deeper question. Why was entropy so low to begin with? For entropy to increase, it has to start from a low value. And the entropy of the early universe, the state of the cosmos in the moments after the Big Bang, was extraordinarily, almost impossibly low, beautifully, precisely, exquisitely ordered relative to what it could have been. The conditions were set up in a way that allowed entropy to increase for billions upon billions of years, giving rise to stars, galaxies, chemistry, life, and eventually creatures capable of noticing that things tend to fall apart. But why? Why did the universe begin in such a low entropy state? That question doesn't have a clean answer within current physics. Some cosmologists, like Roger Penrose, have argued that the initial low entropy of the universe is one of the most profound and underappreciated mysteries in all of science, more fundamental, in a sense, than even the question of dark matter or dark energy. Others have proposed that the low entropy beginning is a natural consequence of the way our pocket universe nucleated from an inflationary background. Others still suggest we need an entirely new framework to even pose the question properly. What everyone agrees on is this: the arrow of time, the thing that makes your life feel like a forward-moving story rather than a static four-dimensional block, is not written into the fundamental laws of physics. It emerges from the particular history and initial conditions of our universe. In some deep sense, the experience of time passing, of the present moment moving forward, of the past being fixed and the future being uncertain, all of that is a consequence of where we happen to find ourselves in the story of a universe that started in an unusually ordered state and has been unwinding ever since. Now, there's a view of time in physics that many people find even more unsettling than that, and it comes directly out of Einstein's theory of special relativity. In special relativity, time is not a universal backdrop against which events unfold. It's a dimension woven together with the three spatial dimensions into a single four-dimensional fabric called space-time. And just as different observers moving through space at different velocities can disagree about distances, a concept most people are comfortable with, they also disagree about time, about the duration between events, about the order in which some events occur. This isn't a measurement error or a perceptual illusion. It's a physical reality, confirmed by every precision experiment ever done to test it. The full implication of this is something called the block universe, or eternalism. In this view, all of space-time exists simultaneously as a four-dimensional structure. The past isn't gone. The future isn't yet to come. Every moment that has ever occurred or will ever occur simply exists, fixed and real, at its particular coordinates in space-time. What we experience as the flow of time, the sense of the present moment moving forward, is not a feature of the universe itself. It's a feature of how conscious observers move through the four-dimensional block. The word now has no universal meaning in this framework. Your now and the now of someone moving relative to you at a significant fraction of the speed of light are different slices through the space-time block. Which one is the real present? Neither and both. The question itself is malformed. Most physicists are comfortable with the mathematical structure of the block universe, whether it reflects as genuine ontological reality. Whether the future truly exists in the same sense the present does, is a question that bleeds from physics into philosophy faster than almost any other in science. And nobody has a fully satisfying answer. Now let's talk about the texture of reality itself. Because in 2023, an experiment delivered results that made a significant number of physicists genuinely uncomfortable. For decades, one of the central debates in the foundations of quantum mechanics has concerned something called quantum entanglement and the nature of what physicists call local realism. Local realism is the intuitive idea that objects have definite properties independent of whether anyone is measuring them, and that no influence can travel faster than light. It sounds completely reasonable. It sounds like the minimum baseline assumption for a sensible universe. John Bell, in 1964, derived a set of mathematical inequalities, now called Bell inequalities, that any locally realistic theory must satisfy. The prediction was stark. If local realism is correct, certain measurements on entangled particles will show correlations only up to a specific limit. If quantum mechanics is correct, those correlations will exceed that limit in a specific, predictable way. Experiments testing Bell inequalities began in the 1980s with Alain Aspect's landmark work in Paris. They showed violations of Bell inequalities. Quantum mechanics was right, local realism was wrong. But those early experiments had what physicists called loopholes, technical assumptions that a sufficiently determined skeptic could use to question the conclusions. Over the following decades, experimentalists worked systematically to close those loopholes, and in 2022, the Nobel Prize in Physics was awarded to Alain Aspect, John Clauser, and Anton Zeilinger for their collective work on entanglement experiments and Bell inequality violations. The committee's citation was unambiguous. Entanglement is real. Local realism is not how the universe works. Our universe is not locally realistic. Either objects don't have definite properties before they're measured, or influences between entangled particles are not constrained by locality, or both. The universe at its most fundamental level does not behave the way common sense demands it should. And no interpretation of quantum mechanics, Copenhagen, many worlds, pilot wave, relational quantum mechanics, cubism, any of them makes this fact go away. They just disagree about what it means. And that brings us to the question that some physicists have started taking seriously in peer-reviewed literature. The one that tends to make people either deeply uncomfortable or strangely excited, depending on their temperament. Could the universe be, in some meaningful sense, informational in nature? Could physical reality, matter, energy, space-time itself, be in some sense computational? Not necessarily in the crude science fiction sense of we're living in a video game, but in a deeper, more mathematical sense, that the substrate of reality might be information and the physical world we experience might emerge from something more abstract underneath. This isn't a new idea. John Wheeler, one of the great physicists of the 20th century, the man who popularized the term black hole, spent the later years of his career arguing for what he called it from bit, the idea that every particle, every field, every space-time event derives its existence from information, from the answers to yes or no questions. that physical reality is, at its root, information theoretic. More recently, physicists like Max Tegmark have argued for what he calls the mathematical universe hypothesis, the idea that our universe doesn't merely use mathematics as a descriptive tool, but that it literally is a mathematical structure, that the difference between the abstract mathematical object and the physical universe is not a difference of substance but of perspective. Our universe exists because it is a consistent mathematical structure, and all consistent mathematical structures exist with equal ontological status. Tegmark's hypothesis is not empirically testable in the conventional sense, but it has remarkable explanatory power for certain puzzles, most notably the unreasonable effectiveness of mathematics in describing physical reality. Why does the universe respond so precisely, so completely, and so reliably to mathematical description? Why does every physical law we've ever discovered turn out to have a clean mathematical form? Tegmark's answer is that it couldn't be any other way, because the universe is mathematics. And then there's the simulation hypothesis, not as a pop culture curiosity, but as a genuine philosophical and scientific argument. The most rigorous version was formalized by philosopher Nick Bostrom in 2003, and it goes like this. If it is possible, in principle, to simulate conscious experience using computational processes, and if sufficiently advanced civilizations tend to run many such simulations, then the number of simulated conscious observers in the universe will vastly outnumber the biological ones. And if you don't know whether you are biological or simulated, the probability that you are simulated is overwhelmingly high. This argument doesn't require the simulations to be perfect. It doesn't require them to simulate every subatomic particle. It requires only that they be sufficient to produce the experiences of the observers within them, which, intriguingly, is somewhat consistent with the way quantum mechanics actually works. In quantum mechanics, physical quantities don't have definite values until they're measured, until they're observed. The universe, in some interpretations, only renders detail when something is looking, which sounds, to some ears, uncomfortably like the behavior of a simulation optimized for computational efficiency. Now, is this science? Is it testable? Some researchers have tried to construct tests. One idea, proposed by Silas Bean and colleagues in 2012, suggests that if the universe were being simulated on a discrete lattice, a grid of finite resolution, it might produce subtle signatures in the distribution of extremely high-energy cosmic rays. The results so far are inconclusive. What's important is not that the simulation hypothesis is correct. It probably isn't, in the most literal sense. What's important is that it's not trivially dismissible, that it emerges from genuine mathematical reasoning about the nature of consciousness and computation, and that it sits within a broader class of questions about why the universe is mathematically structured, why it's fine-tuned for complexity, why it permits observers at all, that physics does not yet have complete answers to. Here's what I find most remarkable about all of this. The deeper you go, the further you push into the foundations of physics, into the nature of time, into the structure of quantum reality, into the question of why the universe exists and why it has the properties it does. The more you find that our best theories, as extraordinarily successful as they are, rest on foundations that haven't been fully secured. We have the standard model of particle physics, the most precisely tested theory in the history of science, confirmed to extraordinary decimal places by experiment, and it doesn't include gravity. We have general relativity, our best theory of gravity, confirmed by every test ever applied to it. And it breaks down at singularities and in the earliest moments of the universe. We have quantum mechanics, the framework underlying all of chemistry, all of materials science, all of modern technology. and after nearly a century, physicists still disagree about what it actually means. These aren't failures, they're the honest map of where human knowledge currently stands. They're the open edges, the places where the known gives way to the unknown, where the questions are sharper than the answers, where the universe is most clearly larger than our current understanding of it. And that's not terrifying, or rather, it is and it isn't. It's terrifying the way standing at the edge of a continent and staring out at an unmapped ocean is terrifying. There's genuine vertigo. There's real uncertainty about what lies beyond the horizon. But there's also the knowledge that the ocean is there to be sailed, that the questions exist to be answered, that every generation of physicists, astronomers, and cosmologists moves that horizon a little further out. We are not at the end of anything. We are somewhere in the middle of the greatest intellectual adventure our species has ever undertaken. Let's talk about what happens when a star dies badly. Not all stellar deaths are equal. A star like our Sun will eventually exhaust its hydrogen fuel, swell into a red giant, shed its outer layers into a beautiful expanding shell of glowing gas called a planetary nebula, and leave behind a slowly cooling ember called a white dwarf, quiet by cosmic standards, dignified almost. But stars significantly more massive than the Sun, roughly 8 times the solar mass and above, don't go quietly, they go catastrophically. When the nuclear fuel in their cores finally runs out, the outward pressure that had been counteracting gravity for millions of years suddenly vanishes. The core collapses, not slowly. In a fraction of a second, somewhere around a quarter of a second, a core roughly the size of Earth implodes to a sphere perhaps 20 to 25 kilometers across. The density reached in that collapse is so extreme that protons and electrons are forced together, combining into neutrons. The entire core becomes essentially a single enormous atomic nucleus, a neutron star, and the outer layers of the star, still falling inward under gravity, slam into this suddenly rigid neutron core and rebound outward in one of the most energetic events in the observable universe, a core collapse supernova. In those few seconds, the exploding star releases more energy than our Sun will emit across its entire 10 billion-year lifetime. Most of that energy, roughly 99%, goes out not as light or heat but as neutrinos, ghostly, nearly massless particles that pass through ordinary matter almost without interaction. In those brief moments, a dying star produces more neutrinos than the Sun emits in 10 billion years, and they travel outward through the collapsing star, essentially unimpeded, carrying the bulk of the explosion's energy with them. The light show, the brilliant optical display that makes supernovae visible across billions of light years, is just the remaining 1%, the leftover, the afterthought of a dying star. What remains at the center, if the progenitor star wasn't massive enough to form a black hole, is a neutron star, and neutron stars are among the most astonishing objects in existence. Picture something containing between 1 and 2 times the mass of our Sun, compressed into a sphere roughly 20 kilometers across. The density at the core of a neutron star is somewhere around 400 million tons per cubic centimeter. That number is essentially impossible to genuinely visualize, but here's a way to approach it. If you could take a single sugar cube and fill it with neutron star material, it would weigh roughly as much as all of humanity combined. Every human being who has ever lived, packed into a volume smaller than a fingernail, at those densities, matter itself behaves in ways we don't fully understand. The neutrons in the core may be squeezed so tightly that they dissolve into their constituent quarks, producing what theorists call strange quark matter or a quark-gluon plasma. Some models suggest the very center of a neutron star may contain exotic states of matter that have never been produced in any laboratory on Earth and may never be. We're genuinely uncertain what the interior of a neutron star looks like at the deepest level. because the physics there pushes beyond what our current equations can confidently describe. The surface of a neutron star is no less extreme. The gravitational field at the surface is roughly 200 billion times stronger than Earth's gravity. The escape velocity, the speed you'd need to leave the surface, is roughly half the speed of light. The surface temperature of a young neutron star can exceed 1 million Kelvin. And that surface, the crust, is composed of a crystalline lattice of atomic nuclei so rigid that it makes the hardest materials on Earth look like wet tissue paper by comparison. And then there are magnetars. Magnetars are a subtype of neutron star with magnetic fields so extreme they represent a category of physical phenomenon that has no analog anywhere else in nature. A typical neutron star has a powerful magnetic field, already far beyond anything generated naturally on Earth. A magnetar's field is roughly 1,000 times stronger than that. We're talking about magnetic fields on the order of 10 to the power of 11 Tesla. For context, the strongest sustained magnetic fields produced in human laboratories reach a few tens of Tesla. A magnetar's field is 10 billion times more powerful. At that field strength, physics becomes alien in the most literal sense. The quantum vacuum itself is affected. The magnetic field is strong enough to polarize the fabric of empty space, causing it to behave like a refractive medium for light. A phenomenon called vacuum birefringence, predicted by quantum electrodynamics but never observed on Earth, actually occurs around magnetars. Light traveling near a magnetar splits into two components that travel at slightly different speeds through the magnetized vacuum, the same way light splits in certain crystals. The ESA's XMM Newton telescope found tentative observational evidence of this effect around a neutron star called RxJ 1856.5-3754 in 2016, marking one of the first times a purely quantum electrodynamic effect had been observed in an astrophysical setting. At a distance of 1,000 kilometers from a magnetar, roughly the distance between two mid-sized cities on Earth, its magnetic field would be strong enough to disrupt the electron orbitals of atoms in your body. The chemistry that makes you function would cease to work. You would not need to touch it or even come anywhere near its surface. The field itself, radiating outward through space, would be enough. Magnetars occasionally undergo what are called starquakes, sudden shifts in the crystalline crust as the enormous magnetic and gravitational stresses reorganize. These starquakes release enormous bursts of gamma rays and X-rays in fractions of a second. On December 27, 2004, a magnetar called SGR 1806-20, sitting roughly 50,000 light-years away on the other side of the Milky Way, underwent a giant flare. In about 0.2 of a second, it released more energy than our Sun emits in 250,000 years. That burst, despite originating 50,000 light-years away, was energetic enough to measurably affect Earth's ionosphere. It ionized the upper atmosphere on the side of Earth facing the magnetar, the same effect produced by solar flares, but from something sitting halfway across the galaxy. Had that magnetar been even a few thousand light-years closer, the consequences for life on Earth's surface could have been significant. The universe contains objects so violent that their tantrums, felt across 50,000 light-years of interstellar space, leave marks on our planet. Now let's talk about what happens when two neutron stars find each other. Neutron stars can exist in binary systems, two neutron stars orbiting each other, bound by mutual gravity. Over time, they lose energy by emitting gravitational waves, exactly the kind of low-frequency ripples we discussed in Part 4, and their orbits slowly decay. They spiral inward, closer and closer, faster and faster, until, after perhaps hundreds of millions of years of slow in spiral, they collide. The result is called a kilonova, and it is one of the most productive and extraordinary events the universe produces On August 17, 2017, gravitational wave detectors LIGO and Virgo detected a signal designated JW170817, the first ever detection of gravitational waves from a neutron star merger. Within seconds, the Fermi Gamma-ray Space Telescope detected a short gamma-ray burst from the same region of the sky. Within hours, optical telescopes around the world and in space had located the source, a galaxy called NGC 4993, about 130 million light-years away. What they observed over the following days was extraordinary. The kilonova glowed bright blue at first, then faded to red over days and weeks. The color evolution told the story of what was being produced. In the cataclysmic collision of two neutron stars, the conditions of temperature and neutron density are so extreme that atomic nuclei are built up rapidly through a process called the R process, rapid neutron capture. Neutrons slam into atomic nuclei faster than those nuclei can decay, building up heavier and heavier elements in a cascade of nuclear reactions that can only occur in environments this extreme. The R process is responsible for producing roughly half of all elements heavier than iron in the universe, elements including gold, platinum, silver, uranium, iodine, barium, and dozens of others, elements that cannot be produced in the cores of ordinary stars and that require the neutron-rich, ultra-energetic environment of a neutron star merger to form. From the single event JW170817, astronomers estimated that the kilonova produced somewhere between 3 and 13 Earth masses of gold alone, tens of Earth masses of other heavy elements, scattered outward into space, eventually to be incorporated into gas clouds, then into new stars, then into the planets and chemistry of future solar systems. The gold in every ring, every necklace, every electronic circuit on this planet, every ounce of gold in Earth's crust, was forged in collisions like that one, not in stars, not in supernovae alone, in the violent, grinding, neutron-saturated collision of dead stellar remnants billions of years ago, in galaxies that may no longer exist in any recognizable form. You are wearing the wreckage of neutron star collisions. The gold on your finger passed through one of the most extreme environments in the observable universe before it became part of your world. Let's push even further, because there's a class of astrophysical event that makes even kilonovae look modest in energy terms, and that's the long gamma-ray burst, specifically the kind produced by the collapse of a rapidly rotating, extremely massive star into a black hole. When a star many times more massive than those that produce ordinary neutron stars collapses, the result isn't a neutron star. The mass is too great, gravity wins completely. A black hole forms directly, but if the progenitor star was rotating rapidly and had the right composition, the infalling material forms a rapidly spinning accretion disk around the newborn black hole, and the magnetic fields generated in that disk launch two focused jets of plasma outward along the rotation axis at velocities exceeding 99.9% of the speed of light. Those jets punch through the collapsing star and emerge from both poles, producing beams of gamma radiation so intense that a long gamma-ray burst can briefly outshine the entire observable universe in gamma rays. Every galaxy, every quasar, every other source of radiation in existence, for anywhere from a few seconds to several minutes, a single dying star in a single galaxy produces more gamma-ray energy than everything else in the observable universe combined. If a long gamma-ray burst were aimed at Earth from within a few thousand light-years, a distance that, cosmically speaking, is essentially next door, it would be devastating. The gamma radiation would strip away the ozone layer on the hemisphere facing the burst, potentially exposing the surface to lethal levels of ultraviolet radiation. Some researchers have proposed that a gamma-ray burst may have contributed to the late Ordovician mass extinction, approximately 440 million years ago, one of the 5 largest extinction events in Earth's history. The evidence is circumstantial, but the physics is sound. The universe has the capacity to reach out across thousands of light years and reshape the trajectory of life on a planet. We've been fortunate. But fortune, in a universe this large and this violent, is not a policy. There's one more object worth talking about in this part of the journey. Something discovered only in 2017 and still not fully explained. Something that arrives from outside the galaxy from cosmological distances, lasting anywhere from a fraction of a millisecond to a few seconds, and carrying more energy in that brief flash than the sun produces in days or weeks. Fast radio bursts, FRBs, they are brief, extraordinarily bright pulses of radio waves originating from billions of light years away. The first was discovered in archival data by astronomer Duncan Lorimer in 2007, a signal from 2001 that had been sitting unrecognized in data tapes for years. Since then, hundreds have been detected, and with new instruments like the Canadian Hydrogen Intensity Mapping Experiment, CHIME, we're now detecting them almost daily. Some FRBs occur once and never repeat. Others repeat, sometimes irregularly, sometimes in patterns that hint at periodicity. The repeating ones have allowed astronomers to localize their sources and identify host galaxies. The leading explanation for most FRBs involves magnetars, those extreme magnetic neutron stars we discussed earlier, undergoing starquakes or magnetic reconnection events powerful enough to produce the observed radio emission. A magnetar in our own galaxy, SGR 1935+2149, produced a radio burst in April 2020 that was detected by multiple observatories simultaneously. The first time an FRB-like event had been caught from a known source within the Milky Way, providing the strongest evidence yet that at least some FRBs come from magnetars, but not all FRBs fit neatly into the magnetar picture. Some have properties that strain the model. Some show signs of propagating through unusual environments. The diversity of observed FRBs suggests there may be more than one type of source, more than one physical mechanism producing these extraordinary bursts. The field is young, the data are accumulating rapidly, and the full story hasn't been told yet. What's certain is that the universe is constantly, relentlessly producing events of staggering energy across all wavelengths of the electromagnetic spectrum, and we are only now, with instruments sensitive enough to catch them, beginning to take inventory of just how violent and dynamic the cosmos truly is. We've traveled far in this video, from the Great Attractor pulling our galaxy through space, through the cosmic web and its impossible structures, into the hearts of black holes, back to the first fraction of a second after the Big Bang, through the nature of time and the texture of quantum reality, and now into the most extreme physical objects and events in the observable universe. But we haven't yet reached the strangest destination on this journey, because in Part 8 we're going to go to the very edge, the literal boundary of everything we can observe, and then we're going to ask what lies beyond it, not speculatively, but as rigorously as current physics allows. We're going to talk about what the James Webb Space Telescope has shown us about the earliest galaxies, and why some of what it's finding is quietly alarming to cosmologists. We're going to talk about the universe's very first light, and we're going to ask a question that sounds simple but has no clean answer. Where did everything come from? If you are still watching, make sure to subscribe and give this video a thumbs up. You will be part of a community that explores the cosmos together. On Christmas Day 2021, a rocket lifted off from the Guiana Space Center in South America and carried into space the most powerful infrared telescope ever built. 25 years in development, $10 billion in cost. A mirror 6.5 meters across, composed of 18 gold-coated hexagonal segments folded origami style to fit inside the rocket's fairing, and then unfolded over 2 weeks in space with a precision that had engineers holding their breath at every step. The James Webb Space Telescope. Within months of beginning science operations, it was sending back images that made astronomers stop and look twice. Not because the images were beautiful, though they were extraordinarily so, but because of what was inside them. Galaxies, fully formed, structurally complex, surprisingly massive galaxies, sitting at distances corresponding to redshifts of 7, 8, 10, 12 and beyond. Meaning we were seeing them as they existed when the universe was only 400 million, 300 million, even as little as 230 million years old. And they were too big, too mature, too developed, too bright. According to the standard model of cosmic structure formation, called lambda CDM, for lambda cold dark matter, galaxies build up gradually over time. Small structures form first, then merge and grow. In the very early universe, you expect to find only small, irregular, gas-rich proto-galaxies, primitive structures, the seeds of what will eventually become the grand spirals and ellipticals we see in the nearby universe. What Webb found instead were galaxies with stellar masses comparable to the Milky Way, sitting at redshifts where our models predicted almost nothing that large should exist yet. One study published in 2023 identified a candidate galaxy, nicknamed the Candy Cane, at a redshift suggesting it existed when the universe was only 350 million years old, with a stellar mass already approaching that of a mature galaxy 10 times older. Others found similar anomalies across multiple fields of view, suggesting these weren't flukes, they were a population. Astronomers started calling them universe breakers, not entirely seriously, but not entirely not. The most careful assessment of the situation is this: the standard model is probably not broken. More likely, some of our assumptions within it need revision. Perhaps early galaxies formed stars far more efficiently than current models predict, converting a higher fraction of their available gas into stars in a shorter time. Perhaps early black holes grew faster, driving more intense star formation through their feedback. Perhaps the initial conditions coming out of inflation seeded slightly more concentrated regions of matter than our models assumed. But probably not broken is not the same as fully explained. And the honest position, held by many working cosmologists, is that Webb is showing us something about the early universe that our current models don't comfortably accommodate. The data is forcing a rethinking, not a revolution, but a serious reassessment of how quickly structure forms in the early cosmos, and that process of reassessment, that willingness to let the data challenge the model rather than forcing the data to fit the model, is exactly how science is supposed to work. It's not a crisis, it's the system functioning as designed, but it is a genuine signal that our understanding of cosmic dawn, the epoch when the first stars and galaxies ignited, is incomplete. Let's talk about that epoch directly, because it's one of the most dramatic chapters in the entire history of the universe, and it's only recently that we've begun to see it clearly. After the Big Bang, the universe cooled rapidly. About 380,000 years in, it cooled enough for electrons and protons to combine into neutral hydrogen atoms for the first time, an event called recombination. The universe became transparent. The photons that had been constantly scattering off free electrons were suddenly free to travel unimpeded through space. Those photons are what we see today as the cosmic microwave background, the oldest light in the universe, a snapshot of the cosmos at 380,000 years old, redshifted by the expansion of space from a hot orange glow to microwave radiation, barely above absolute zero. After recombination, the universe entered a period called the Cosmic Dark Ages. There were no stars yet, no galaxies, no sources of light of any kind, just an expanding, cooling, largely uniform sea of neutral hydrogen and helium, threaded with the subtle density variations that inflation had seeded and that gravity was slowly amplifying. For perhaps 200 million years, the universe was genuinely dark, silent, structureless on any human scale. Then gravity did its patient work. The denser regions, the seeds left by quantum fluctuations during inflation, now grown by hundreds of millions of years of gravitational attraction, began to collapse. The first stars ignited. We call this epoch cosmic dawn, and the first stars, designated population 3 stars by astronomers, were almost certainly nothing like the stars we see today, because in the early universe there were no heavy elements, no carbon, no oxygen, no iron, no silicon. The only materials available were hydrogen and helium, with trace amounts of lithium, the elements forged in the first few minutes after the Big Bang through a process called Big Bang nucleosynthesis. Without heavy elements to help radiate away heat during collapse, the gas clouds that formed the first stars couldn't fragment as efficiently. They grew larger, far larger. Population 3 stars are theorized to have been anywhere from tens to potentially hundreds of times the mass of the Sun. Blue-white behemoths burning ferociously hot, living fast, and dying violently in just a few million years. In their deaths, through supernovae and direct collapses into black holes, they seeded the surrounding gas with the first heavy elements ever to exist in the universe. Carbon, oxygen, nitrogen, silicon, iron, the building blocks of planets, of chemistry, of life, were born in the deaths of those first monstrous stars. Every subsequent generation of stars formed from gas already enriched by those early supernovae, and each successive generation added more heavy elements, building up the chemical complexity of the cosmos layer by layer over billions of years. You are the product of that process. The atoms in your body were forged across multiple stellar generations in the cores of stars that lived and died long before the Sun existed, in supernova explosions that scattered their material across light years of space, in neutron star collisions that produced your gold and your iodine and the uranium in Earth's crust. You are not separate from the cosmos. You are a temporary, extraordinarily complex arrangement of material that the cosmos built over nearly 14 billion years, that is right now aware of itself and looking back at the process that produced it. That is not a metaphor, that is literally, chemically, physically true. Now, let's go to the edge, the actual boundary of what we can see. The observable universe extends about 46 billion light-years in every direction from Earth. That might seem strange. If the universe is only 13.8 billion years old, how can we see things 46 billion light-years away? Because space itself has been expanding the entire time the light was traveling. The galaxy that emitted the most distant light we can detect was much closer when it emitted that light, but by the time the photons arrived, the expansion of space had carried that galaxy far beyond its original distance. The 46 billion light-year figure accounts for that expansion. At the very edge of the observable universe, we see the cosmic microwave background, the glow of recombination. 380,000 years after the Big Bang, there is no older light to see. The universe before recombination was opaque. Photons couldn't travel freely, so the CMB represents a genuine wall, a horizon beyond which electromagnetic radiation cannot bring us information, no matter how powerful our telescopes become. But beyond that horizon, the universe continues. We know this because there's no physical reason for the universe to end at the boundary of what we can observe. Our observable bubble is defined not by any property of the cosmos, but by the finite speed of light and the finite age of the universe. Somewhere beyond 46 billion light-years, in regions causally disconnected from us, regions whose light has never and will never reach us, space continues, matter continues, galaxies, stars, and quite possibly other forms of structure and complexity continue. How far does it go? We don't know. The universe might be finite, with a geometry that curves back on itself the way the surface of a sphere does, so that if you traveled far enough in one direction, you'd eventually return to where you started, like an ant walking around a globe. Or it might be infinite, extending without limit in all directions, containing an infinite number of galaxies, an infinite amount of matter, and, depending on your interpretation of probability, in infinite spaces, an infinite number of regions statistically identical to our own observable universe. An infinite universe implies something deeply strange. If matter is distributed randomly across infinite space, and if the number of possible configurations of matter in any given region is finite, as quantum mechanics suggests, then every possible arrangement of matter that can exist must exist somewhere, including in principle exact duplicates of our observable universe, exact duplicates of Earth, of you, of this moment, not copies that are nearly identical, exact copies, quantum state for quantum state, separated by distances so vast they make the observable universe look like a speck. This isn't mysticism. It's a straightforward consequence of infinity and combinatorics. If you shuffle a deck of cards infinitely many times, every possible ordering must eventually appear, and appear infinitely many times. Scale that logic up to the level of the quantum states of the observable universe, and the mathematics points toward something profoundly destabilizing to ordinary intuition. This level of the multiverse, what physicist Max Tegmark calls a level 1 multiverse, doesn't require any exotic new physics. It requires only that the universe be spatially infinite, and that matter be distributed on large scales according to the same statistical patterns we observe locally. Both of those conditions are consistent with everything we currently know. Now let's ask the hardest question, the one that every other question in this script has been quietly building toward. Where did everything come from? Not the Big Bang. We've discussed the Big Bang. The question is what preceded it, or more precisely, what gave rise to it. Because the Big Bang, as our most successful cosmological model, describes the evolution of the universe from an extremely hot, dense state. It doesn't, on its own, describe the origin of that state. It doesn't tell us why there was something rather than nothing. It doesn't tell us what lit the fuse. Several serious theoretical frameworks attempt to address this. Let's go through the most significant ones. The first is the Hartle-Hawking no-boundary proposal, developed by James Hartle and Stephen Hawking in 1983. In this framework, the universe has no boundary in time, no singular beginning in the conventional sense. Using a mathematical technique called Euclidean quantum gravity, they showed that it's possible to describe the quantum state of the universe in a way where time itself smoothly rounds off near the Big Bang, the way the surface of a sphere rounds off at the South Pole. There is no edge, no moment before which something had to exist to cause the universe. The universe simply is, a self-contained quantum system with no external cause required. Hawking was fond of saying, "What was there before the Big Bang? Nothing, because there was no time before the Big Bang. Not nothing in the sense of an empty void, sitting and waiting, but the absence of the very framework in which the concept of before has meaning. This is intellectually satisfying in some ways, and deeply strange in others. It relocates the mystery rather than eliminating it. Why does this particular no-boundary quantum state exist? Why does anything exist rather than nothing at all? The no-boundary proposal is a description of the universe's quantum state, but it doesn't tell us why that state exists rather than no state at all. A different approach comes from string theory and its related framework, M-theory. In certain brainworld cosmologies, models in which our universe is a three-dimensional membrane embedded in a higher dimensional space, the Big Bang might not be a beginning at all. It might be a collision, two membranes existing in a higher dimensional bulk space, drifting toward each other and colliding. The energy released in that collision floods the membrane that is our universe with heat and radiation, what we observe as the Big Bang. In the cyclic models proposed by Paul Steinhardt and Neil Turok, this process repeats. Branes collide, universes are born, expand, cool, and eventually undergo another collision, an eternal cycle of cosmic birth and expansion, with no ultimate beginning and no final end. These models make specific predictions about the character of primordial gravitational waves that differ from those made by inflationary models. As gravitational wave astronomy matures, as the sensitivity of pulsar timing arrays and future space-based detectors like LISA improves, it may eventually become possible to distinguish between these scenarios observationally. We may one day have data that tells us not just how the universe evolved, but something about the conditions that preceded it. That possibility that the question of cosmic origins might be empirically addressable would have seemed almost absurd to physicists a generation ago. Today, it's a genuine scientific prospect, however distant. And then there's perhaps the most radical position of all, the one that some physicists have been pushed toward not by preference but by the mathematics itself. What if the question, why is there something rather than nothing, is malformed? What if nothing, a state of complete absence, no space, no time, no laws, no quantum fields, no mathematical structure, is not actually a stable or even a coherent possibility? What if existence in some deep sense is the default? What if the laws of quantum mechanics, which permit and even require fluctuations in the vacuum, which describe a universe where empty space is never truly empty, imply that the absence of a universe is less stable than the presence of one? This is the line of thinking explored by physicists like Lawrence Krauss in his book A Universe from Nothing, though Krauss is careful to acknowledge that his nothing is a quantum vacuum, which is itself something, not the absolute philosophical nothing. The honest answer is that the question of why there is something rather than nothing may require a framework that transcends both current physics and current philosophy. It may require a theory of everything, a complete unified description of all physical law that we do not yet have, or it may be a question that, in principle, admits no answer within any formal system of knowledge. Kurt Gödel showed in 1931 that within any sufficiently complex formal system, there are true statements that cannot be proven within that system. It is at least conceivable that the question of ultimate origins is, in some analogous sense, a true question that no physics, however complete, can fully answer from the inside. We might be asking, from within the universe, why the universe exists, and the universe may not contain within itself the information needed to answer that question. That's the edge. Not a wall with a door, not a mystery that's simply waiting for the right experiment. Possibly, the genuine boundary of what any observer embedded in physical reality can ever know. And yet, here we are, 13.8 billion years after whatever it was that began this story, on a small rocky planet, with brains evolved to hunt and gather and survive, somehow capable of asking questions about the origin of space-time itself, somehow capable of building telescopes that see to the edge of the observable universe, somehow capable of detecting gravitational waves from neutron star mergers 130 million light-years away, somehow capable of photographing the shadow of a black hole 6.5 billion times the mass of the Sun. The universe produced something that can look back at itself and ask why. Whatever answer eventually comes, or doesn't, that fact alone is extraordinary beyond any easy description. Let's talk about what comes next, because everything we've discussed in this journey, the cosmic web, the black holes, the neutron stars, the gravitational wave background, the edge of the observable universe, the question of origins, all of it represents where human knowledge stands right now. Today, in this particular moment of the scientific story. And that story is nowhere near its final chapter. In fact, if the history of astronomy teaches us anything, it's that the most transformative discoveries tend to come not from confirming what we already suspect, but from the moments when a new instrument opens a new window on the cosmos and shows us something nobody predicted. The CMB wasn't predicted before it was discovered. Pulsars weren't predicted. Fast radio bursts weren't predicted. The accelerating expansion of the universe wasn't predicted. Gravitational waves from a neutron star merger being simultaneously detected in light wasn't predicted to happen as soon as it did. The universe has a persistent habit of being more surprising than our best preparations for it. So what are we preparing for? What instruments are we building right now, aimed at which questions, with what realistic hope of breakthrough? Let's start on the ground. High in the mountains of Chile's Atacama Desert, construction is underway on what will be the largest optical and near-infrared telescope ever built. The extremely large telescope, and yes, that is its actual official name, is being developed by the European Southern Observatory. Its primary mirror will be 39 meters across, nearly 4 times the diameter of the largest existing optical telescopes. Its light collecting area will be roughly 100 times greater than the Hubble Space Telescope. What does that mean in practice? It means the ELT will be capable of directly imaging the atmospheres of Earth-sized planets orbiting nearby stars, not inferring atmospheric composition from indirect measurements, directly detecting the spectral signatures of molecules in those atmospheres: oxygen, water vapor, methane, carbon dioxide, the chemical fingerprints of geological activity and potentially of biology. If there is a planet within a few tens of light years of Earth with an atmosphere bearing the unmistakable chemical signature of life, what astrobiologists call a biosignature, the ELT will have the sensitivity to detect it, not guarantee it, not certainly find it. But for the first time in history, we will have an instrument capable of asking the question empirically rather than theoretically. We will be able to look at specific planets around specific stars and read their atmospheric chemistry from here. The ELT is expected to see its first light around 2028. And what it might tell us about planetary atmospheres, about the formation of the first stars, about the detailed structure of galaxies in the early universe, represents one of the most anticipated openings of a new observational chapter in generations. Meanwhile, in the radio sky, another revolution is quietly unfolding. The Square Kilometre Array, the SKA, is a radio telescope project of genuinely unprecedented scale. Rather than a single dish, it's an array of thousands of individual antennas spread across 2 continents, thousands of low-frequency antennas in the flat desert of Western Australia, and thousands of mid-frequency dishes spread across the Karoo region of South Africa. When combined, they'll function as a single radio telescope with a collecting area approaching 1 square kilometre, roughly the size of 140 football fields. The SKA will probe the cosmic dark ages. Using the 21-centimeter emission line of neutral hydrogen, the faint radio signal emitted by hydrogen atoms, it will map the distribution of gas across the universe during and before cosmic dawn. We'll be able to trace, in 3 dimensions, how the first stars and galaxies gradually ionized the surrounding intergalactic medium and ended the dark ages. We will see in unprecedented detail the reionization of the universe. The moment the cosmos lit up for the first time, the SKA will also dramatically expand pulsar timing array capabilities. With thousands of pulsars monitored simultaneously at extraordinary precision, it will sharpen our map of the gravitational wave background enormously. potentially resolving individual contributions from specific supermassive black hole binaries and pushing sensitivity toward the regime where primordial gravitational waves from inflation might leave a detectable imprint. If the universe whispered something at its birth, a gravitational echo of inflation itself, the SKA might be sensitive enough to hear it. In space, two missions deserve particular attention. The Nancy Grace Roman Space Telescope, named after NASA's first chief of astronomy, often called the Mother of Hubble, is scheduled for launch around 2027. Its wide field of view is roughly 100 times larger than Hubble's, allowing it to survey enormous swaths of the sky in infrared light with extraordinary depth and precision. Among its primary science goals, mapping the large-scale structure of the universe with enough detail to precisely constrain the properties of dark energy. By measuring the distribution of galaxies across cosmic time with far greater statistical power than any previous survey, Roman will help determine whether dark energy is truly a cosmological constant, fixed and unchanging, or whether it evolves over time. That distinction matters enormously. If dark energy is constant, it fits the mathematical description of the quantum vacuum energy, however poorly we understand its magnitude. If it evolves, if its strength or character changes across cosmic time, it points towards something more dynamic, a new field, a new physics, something currently outside our theoretical frameworks entirely. Roman may also detect thousands of new gravitational lensing events, illuminate the distribution of dark matter halos across the universe, and, through its microlensing survey toward the galactic bulge, find hundreds of planets around distant stars, including potentially free-floating planets ejected from their solar systems and drifting alone through interstellar space. And then there is LISA, the Laser Interferometer Space Antenna, approved by the European Space Agency with NASA participation and targeted for launch in the mid-2030s. LISA will be the first dedicated space-based gravitational wave detector. It will consist of 3 spacecraft flying in a triangular formation, separated by 2.5 million kilometers, connected by laser beams that measure tiny changes in distance caused by passing gravitational waves. The frequency range LISA is designed to detect, lower than LIGO, sitting between roughly a 10,000th and a tenth of a hertz, is rich with sources that ground-based detectors can't access. Millions of compact binary systems in our galaxy, supermassive black hole mergers at cosmological distances, events so energetic that a single merger could be detectable from virtually anywhere in the observable universe, and, potentially, the gravitational wave background itself, that cosmic hum we discussed in Part 4, at frequencies where LISA will have exquisite sensitivity. LISA could detect the merger of 2 supermassive black holes months before it happens, giving astronomers time to prepare every available telescope on Earth and in space to observe the event simultaneously across the entire electromagnetic spectrum. The multi-messenger astronomy that made GW 170817 so extraordinary that simultaneous detection of gravitational waves and light from a single neutron star merger could become routine, extended to the most massive and energetic events in the universe. We are building, piece by piece, instrument by instrument, a truly multi-messenger observatory for the cosmos. It's a system that can hear the universe in gravitational waves, see it across the full electromagnetic spectrum from radio to gamma rays, and taste it in the neutrinos and cosmic rays that arrive continuously from across the galaxy and beyond, each messenger carrying different information, each opening a different window, together building a picture of cosmic reality more complete than any single instrument could ever provide. But there's a question that sits behind all of these instruments and all of these planned observations. A question that doesn't get asked often enough in discussions about the future of astronomy. And it's this: what are we actually hoping to find? The optimistic answer, and I think the honest one, is that we're hoping to find things we didn't expect. That's been the engine of progress in every significant era of astronomical discovery. Not the confirmation of what was already suspected, but the surprise, the anomaly, the signal that doesn't fit, the image that shows something where nothing was predicted. The measurement that comes back with the wrong number. Surprises are how science grows, not through the orderly accumulation of expected results, but through the moments when the universe refuses to behave the way the model said it should. And right now, today, there are several active anomalies in cosmology and astrophysics that might be the seeds of the next revolution. We've mentioned some of them: the Webb early galaxy problem, the cold spot, the gravitational wave background's precise character. But there's one I haven't mentioned yet, and it's perhaps the most statistically significant tension in all of modern cosmology. It's called the Hubble tension. Here's the issue. The Hubble constant, the number that describes the current rate of expansion of the universe, expressed in kilometers per second per megaparsec, can be measured two independent ways. The first way uses the cosmic microwave background and the early JWST physics encoded in it, combined with the standard cosmological model to predict what the Hubble constant should be today. This method, using data from the Planck satellite, gives a value of approximately 67.4 kilometers per second per megaparsec. The second way measures the Hubble constant directly in the local universe using a chain of distance measurements called the cosmic distance ladder, anchored to Cepheid variable stars and Type IR supernovae. This method, refined over decades and led most prominently by Adam Rees and the SH0ES collaboration, consistently gives a higher value, around 73 kilometers per second per megaparsec. These two numbers disagree, not trivially, by a statistically significant margin that, as measurement precision has improved over the years, has refused to go away. It has reached a significance level of roughly 5 sigma, the traditional threshold in physics for claiming a discovery. The probability of this discrepancy arising by chance, given the stated measurement uncertainties, is less than 1 in a million. Something is wrong. Either one or both measurement methods have unidentified systematic errors, or the standard cosmological model is missing something. Some new physics, perhaps a brief period of early dark energy that modified the universe's expansion in the time before recombination, or new interactions in the dark sector, might reconcile the two measurements. Dozens of proposed solutions have been published. None has yet achieved consensus. The tension remains. And if it's real, if it genuinely points to new physics rather than measurement error, it could be the crack in the standard model through which something completely new eventually enters. It wouldn't be the first time. The anomalous precession of Mercury's orbit was a small, persistent discrepancy in Newtonian gravity that took decades to explain, and the explanation was general relativity. Small, stubborn, well-measured anomalies have a habit of pointing toward large transformative revisions. Now, I want to step back from the instruments and the measurements and the open questions for a moment, because I think there's something worth saying that doesn't get said clearly enough in discussions like this one. Every person who has ever looked up at the night sky and felt something, wonder, smallness, curiosity, a vague and nameless pull toward the darkness and the light, has been participating in the oldest human activity there is. Before science, before language, before civilization, we looked up, we tried to make sense of what we saw, we told stories about it, we navigated by it, we built our calendars around it, we oriented our temples toward it. We wrote it into our mythologies and our mathematics and our music. The science we've built to understand the cosmos, the telescopes and detectors and theoretical frameworks, is the most recent and most powerful expression of that same ancient impulse. It doesn't replace the wonder, it deepens it. Every time we resolve a mystery, we expose 10 more. Every time we open a new window on the universe, we discover that the view is richer, stranger, and more profound than the previous window suggested. Carl Sagan wrote, decades ago, that we are a way for the cosmos to know itself. That line has been quoted so many times it risks becoming a cliché, but I want you to actually sit with it for a moment, not as a pretty turn of phrase, as a literal description of what is happening right now. The atoms in your brain, the carbon, oxygen, hydrogen, nitrogen, phosphorus, were forged in stellar cores and scattered by stellar explosions across billions of years. They assembled, through chemistry and biology and evolution, into a structure capable of conscious experience. And that structure, you, is right now processing information about the same cosmos that produced it. You are the universe in a very real material sense, turning its attention on itself, asking about its own origins, marveling at its own scale, sitting with the discomfort and the exhilaration of its own incomprehensibility. That's not just poetic, that's the actual situation. And here's what I think that situation demands of us. Not passivity, not comfortable awe from a safe distance, engagement, active, curious, relentless engagement with the questions, not just the cosmological ones, though those matter enormously, but the daily questions too. Why does this work the way it does? What's the evidence? What would change my mind? What am I missing? The scientific habit of mind, the one that built the telescopes and derived the equations and detected the gravitational waves, is not something that belongs only to physicists and astronomers. It's a human capacity. It's available to anyone willing to cultivate it. And in a world where the quality of our collective decisions depends increasingly on our ability to reason carefully about complex systems, climate, technology, biology, economics, that capacity matters more than it ever has. Looking up at the cosmos isn't an escape from the world, it's a reorientation within it. It reminds you how contingent everything is, how brief, how extraordinary it is that any of this exists at all, that we're here at all, that we're capable of asking any of these questions at all. You live on a pale blue dot, as Sagan called it, orbiting an average star in the outer spiral arm of one galaxy among hundreds of billions in a universe 13.8 billion years old. That may be one of infinitely many whose ultimate nature and origin we don't fully understand, whose fate is a cold and silent darkness tens of orders of magnitude of years from now. And right now, in this sliver of cosmic time, you are here, conscious, curious, capable of wonder. That is not nothing. In the context of everything we've discussed, in the context of the vast, violent, mostly empty, largely dark cosmos we've traveled through together, that might be the most remarkable thing of all. Let's come home. We've traveled far in this video, further, in some ways, than any physical journey could take you. We started with our galaxy being hauled through space towards something we can barely see. We moved outward through the cosmic web, those vast filaments and walls and voids that give the universe its large-scale skeleton. We fell toward black holes and sat with the paradoxes they generate. We went back to the first fraction of a second after the Big Bang, listened to the gravitational hum running through all of space-time, confronted the mystery of dark matter and the unsettling implications of dark energy. We visited neutron stars dense enough to break physics, watched two of them collide and forge the gold in your jewelry, stood at the edge of the observable universe and asked what lies beyond it. We questioned the nature of time, the texture of quantum reality, and the deepest question of all, why anything exists rather than nothing. That's a lot to carry, and I want to spend this final part not adding more weight, but helping you make sense of what we've already gathered. Because I think there's a perspective that emerges from all of it. Not a conclusion exactly, but an orientation. a way of standing in relation to the cosmos that is both honest about its strangeness and genuinely sustaining. Let me try to articulate it. The first thing worth sitting with is this: everything we've discovered about the universe, every finding that made it feel more vast, more violent, more indifferent, more incomprehensible, has also, without exception, made it more interesting, more layered, more worthy of attention. The universe we thought we lived in before modern astronomy was smaller and simpler. The stars were lights fixed in a dome. The Earth was the center. Time was absolute. Matter was made of indivisible atoms moving through empty space according to clean mechanical laws. That universe was comprehensible in a way ours isn't, and it was impoverished by comparison. Flat in the way a map is flat. Technically useful, fundamentally incomplete. The universe we actually live in, the one we've been describing together, is not flat. It is dizzyingly, almost offensively deep. Every layer you peel back reveals another layer beneath it. Every question answered opens three more. The further you look, the stranger it gets. And that strangeness is not a defect, it's a feature. It's the universe being exactly as rich as it needed to be to produce stars, chemistry, biology, consciousness, and the very curiosity that's making you ask questions about it. The incomprehensibility isn't a wall, it's an open door. Let me revisit something from early in this video. The Great Attractor, that enormous concentration of mass sitting roughly 250 million light-years away, pulling our galaxy and dozens of others through space at roughly 600 kilometers per second, hidden for decades behind the plane of our own galaxy. When we first talked about it, I framed it the way it often gets framed, as something unsettling, something pulling us toward it, something we can barely see, something we don't fully control or understand. And all of that is true. But here's the other way to see it. We found it. Despite it hiding almost perfectly behind the densest, most optically opaque region of our own galaxy, despite having no direct line of sight to it in visible light, we found it anyway, using X-ray telescopes, radio observatories, and careful analysis of the motions of thousands of galaxies. We mapped something 250 million light-years away that we can't directly see. We deduced its existence and approximate structure from its gravitational fingerprint on the matter around it. That is an extraordinary thing for a species to be able to do. For creatures that evolved on a small planet, who've been doing organized science for only a few centuries, who only recently learned that other galaxies even exist, to be able to identify a structure 250 million light-years away by reading its effect on the motion of matter around it, that is not a small achievement. That is one of the most remarkable things any known form of intelligence has ever accomplished. We should feel that. Not just as abstract pride, but as genuine, embodied astonishment at what careful, patient, honest inquiry can achieve. Now, here is something I want to say carefully, because I think it's important and it's often either overstated or understated. The universe is not designed for us. The evidence does not support that reading. The cosmos is approximately 13.8 billion years old, and for the vast majority of that time, it contained no life of any kind, only hydrogen and helium slowly assembling under gravity into the first stars, those stars living and dying and enriching the surrounding gas with heavier elements over billions of years before the conditions for chemistry and biology became available anywhere. The universe is unimaginably vast, and the overwhelming majority of it, the voids, the radiation fields, the surfaces of neutron stars, the regions near active black holes, is instantly lethal to any form of life we know. The universe, in any straightforward sense, does not care about us. And yet, and this is the part that I think deserves to be said as carefully and as clearly as possible, we are not accidental in a way that makes us meaningless. Those are two completely different things. and conflating them is one of the most common and costly errors in thinking about our place in the cosmos. We are the outcome of a process that took nearly 14 billion years, a process that required the deaths of multiple generations of stars, a process that required the precise values of physical constants, the strength of gravity, the electromagnetic force, the parameters of nuclear physics, to fall within narrow ranges that permit atoms, molecules, chemistry, and biology. A process that required billions of years of biological evolution on a planet sitting at the right distance from a star of the right type, with the right chemical composition, with the right geological activity to cycle carbon and regulate temperature. That process wasn't designed, but it happened, and its result, you, conscious and curious and capable of asking why, is genuinely extraordinary, not because something intended it, but because it occurred despite requiring so many things to go right, across such enormous spans of time and space that its occurrence is remarkable on its own terms, without any need for external intention to make it so. You don't need the universe to have been designed for you in order for your existence to be astonishing. The fact that it happened without design makes it, in some ways, more astonishing, not less. Let's talk about what the scale of the universe actually means for how you live. One response to everything we've discussed, a very common one and a completely understandable one, is to feel small. To feel that in the face of a universe 460 billion light-years across, containing hundreds of billions of galaxies that will exist for trillions upon trillions of years, after the last human being draws the last human breath. In the face of all that, what could any individual life possibly matter? What difference does any of it make? What's the point of anything? I want to take that feeling seriously, because it's not irrational. It's a genuine response to genuine information. The scale is real. The indifference of the cosmos to individual human lives is real. The brevity of our time here, relative to the timescales we've been discussing, is real. But I think the conclusion people draw from that feeling, the slide from I am small relative to the cosmos to I am therefore insignificant, contains a hidden assumption that doesn't hold up. It assumes that significance is a function of size. That bigger means more important. That longer means more meaningful. And when you examine that assumption, it dissolves almost immediately. A supermassive black hole is enormously bigger than a human brain. It is also, as far as we know, completely unconscious. It processes no information about itself. It forms no models of the universe. It feels no wonder. It discovers nothing. It loves nothing. It is mass and gravity and the geometry of curved space-time, extraordinary in its way, but utterly blind to its own existence. The human brain, 1.4 kilograms of electrochemical tissue, generating roughly 20 watts of power, contains approximately 86 billion neurons, forming roughly 100 trillion connections. It builds models of reality. It creates language and mathematics and music. It experiences joy and grief and curiosity. It looks at a black hole 6.5 billion times the mass of the Sun and figures out how to photograph its shadow. Which of those is more interesting? Which is doing more with what it has? Size is not significance. Longevity is not meaning. What you are matters more than how large you are or how long you last. Here's something else the universe has quietly been telling us through every discovery we've made about it. Reality rewards inquiry. Every time we built a better telescope, we saw something new. Every time we developed a more sensitive detector, we found something unexpected. Every time we pushed a theory to its limits, we discovered either that it held up, which was informative, or that it broke, which was even more informative. The universe has never once responded to careful, honest investigation by becoming boring, by running out of depth, by saying essentially, that's it, that's everything, you've found the bottom, there is no bottom, Every bottom we've ever thought we found turned out to be a floor above a deeper room. Atoms turned out to contain nuclei. Nuclei turned out to contain protons and neutrons. Protons and neutrons turned out to contain quarks. Quarks may themselves be vibrating strings of energy in higher dimensions. We don't know yet. Every scale of reality we've examined has turned out to be inhabited by structure, by pattern, by something worth understanding. That is, I would argue, one of the most practically useful things the universe has ever told us, because it means the effort of understanding is never wasted. The questions are never exhausted. There is always more, always something further, deeper, stranger, more beautiful, waiting for the next generation of instruments and ideas and minds willing to look. And now I want to say something about the people doing the looking, the scientists, the astronomers, the physicists, the engineers, the data analysts, the theorists, the human beings who built the Event Horizon Telescope and synchronized it across continents to photograph a black hole, who built LIGO and detected a ripple in space-time 4/1000ths the diameter of a proton, who launched Webb and unfolded it perfectly in space after 25 years of work, who sat with pulsar data for years looking for a signal that everyone hoped was there, but nobody was certain of, until the pattern finally emerged unmistakably from the noise. These people are not superhuman. They are not a special category of being separate from the rest of humanity. They are curious people who cared enough about a question to devote years of their lives to it, who were willing to be wrong and try again, who built on the work of previous generations and left their own contributions for the next ones, who found community and purpose and genuine joy in the pursuit of understanding. That is available to you, not necessarily in the form of a career in astrophysics, though that path is open to anyone willing to walk it, but in the form of the attitude, the disposition, the willingness to ask questions seriously, to follow them honestly, to change your mind when the evidence demands it, and to find in the difficulty of a hard question not frustration but excitement. That's what science actually is at its core, not a collection of facts, an approach to reality, a commitment to asking and a willingness to be surprised by the answers. So let's end where we started, with you sitting here on a small rocky planet being pulled through space at 600 kilometers per second toward a concentration of mass we can barely see, orbiting a star in the outer arm of a galaxy that is itself one of hundreds of billions, in a universe that is expanding faster every moment, that began in conditions our best theories can't fully describe, that is made mostly of things we can't directly detect, that will end in cold and uniform darkness unimaginably far in the future. All of that is true. Every word of it is supported by evidence, confirmed by measurement, cross-checked by independent methods, and as close to certain as science can get, and also true, simultaneously, without contradiction, is this: you are here, right now, in possession of a conscious mind capable of grasping all of the above, living in the one brief window of cosmic time when the universe is young enough to still contain stars and planets and the chemistry of life, old enough to have produced creatures capable of understanding their own situation, and equipped with instruments powerful enough to see to the edge of everything that can be seen. You are not a bystander to the universe. You are an expression of it, a temporary, extraordinarily improbable, unrepeatable expression of a process that has been running for nearly 14 billion years. You are what happens when hydrogen has enough time and enough space and enough violence and enough chemistry to become something that wonders about itself. And what you do with that, what questions you ask, what you build, what you understand, what you pass on to the people who come after you, that is not nothing. In a universe that contains no inherent meaning, the meaning you make is the only kind there is, and it is real, it is yours, and it matters precisely as much as you decide it does. We've been to the edge of everything observable together. We've stood at the boundary of what current physics can describe and looked into the fog beyond it. We've confronted the violence and the strangeness and the loneliness and the grandeur of a cosmos that is, in every direction we point our instruments, more extraordinary than we expected. And we've found, at the end of that journey, that the most remarkable thing in all of it isn't out there. It's the fact that anything is in here at all, that the universe produced observers, that those observers built science, that science keeps finding things worth knowing, that you are one of those observers, and you haven't stopped looking. Don't stop looking. The universe has more to show you than you can possibly imagine. And the best discoveries, the ones that will genuinely reshape what it means to be a thinking creature on this particular planet at this particular moment in cosmic history, haven't been made yet. They're waiting. Out there, in the data we haven't collected yet, in the frequencies we haven't listened to yet, in the mathematics we haven't written yet, in the minds of people who haven't yet asked the question that will change everything. Maybe one of them is yours. Keep asking, keep looking, keep going deeper, because the deeper you travel into space, into the real documented, telescope-confirmed, peer-reviewed space that we've explored together today, the more terrifying it gets and the more beautiful. And if this video left you feeling the weight of just how impossibly far everything is, you need to watch this next. Even if we cracked warp drive tomorrow, the distances between stars are so brutal that it still might not be enough. That video is on your screen right now. Click it. You won't look at space travel the same way again.